plane geometrically, if reflection through an external mirror plane generates a new molecule that's identical to the starting molecule, then there ought to be an internal mirror plane, an internal plane of reflection, such that reflection through that plane leaves the molecule completely unchanged in appearance. So for example, consider ethanol, which is the top left example on this slide. If we think about reflection through the plane of the screen, well, many of the atoms in ethanol are in the plane of the screen. That includes, for example, the hydrogen, the oxygen, this carbon, and even one of the hydrogens on the methyl group are all within this plane I've outlined in green. The only atoms that are out of the plane are two of the hydrogens on the CH3 group, and the wedged hydrogen here, and the dashed hydrogen here. And if you imagine reflecting through the plane of the screen, you'll see that this reflection only exchanges the positions of those two hydrogens and does the same thing to the two hydrogens above and below the plane on this methyl group. So for ethanol, as it's drawn right here, reflection through the plane of the screen leaves the appearance of the molecule completely unchanged. In other words, the green plane is what's known as a plane of symmetry. It's an internal mirror plane, reflection through which leaves the appearance of the molecule completely the same. Atoms may have exchanged positions, but because the atoms don't carry labels with them, as long as they're the same type and nothing looks different, nothing really has changed. Just as in the fail-safe method, we concluded that a molecule was achiral if reflection through an external mirror plane generated the same molecule. If we find an internal plane of symmetry within a molecule, we can immediately conclude that it is achiral. This method is equivalent to the fail-safe method. However, it relies on your ability to identify planes of symmetry within molecules and do this mental operation of reflection through an internal mirror plane. Though you won't need to rotate the structure after reflection through a plane of symmetry to verify that it's the same as what you started with, you will need to be flexible about where you position the plane of symmetry. It could be in any of the three sort of Cartesian planes or even at an angle. So let's work through these examples to see if we can identify planes of symmetry within achiral molecules and discuss how we negotiate chiral molecules and their lacks of planes of symmetry, which can be a little bit difficult to recognize. Let's start with the heterocycle right below ethanol right here. We already know from the fail-safe method that this is an achiral molecule, and so it ought to have a plane of symmetry somewhere within its structure. Remember that we noted in the last video that all of the atoms in this molecule are coplanar, and that includes the implicit hydrogens. The two hydrogens on nitrogen are coplanar because that nitrogen is sp2 hybridized. Make sure you understand why. Same idea here. This nitrogen is sp2 hybridized, and therefore its hydrogen is also in the same plane as all of the other atoms, as are all of the other hydrogens. They all sit within the same plane. Since all of the atoms are coplanar, that means that the plane of the molecule is a plane of symmetry, and this is true for every molecule that's completely planar. The plane of all of the atoms of the molecule is a plane of symmetry. Reflection through that plane just flips the atoms upside down. It doesn't change their positions in space. Therefore, that's got to be a plane of symmetry. True for every molecule that's completely planar. Another good example of this would be something like carbonate. Carbonate is CO3 2-, and the carbon and the three oxygen atoms all sit in one plane. Therefore, the plane in which all the atoms sit is a plane of symmetry, and carbonate is, of course, an achiral molecule. Let's look at the bottom right case now, which we also identified in the last video as achiral. Where is its plane of symmetry? This molecule is a nice illustration of the idea that planes of symmetry won't necessarily show up in the plane of the screen or even perpendicular to the screen and perfectly vertical or perfectly horizontal. You may need to look for planes of symmetry that are at an angle to each other. To begin doing this, to begin honing your visual apparatus, the first thing I recommend doing is identifying corresponding groups, corresponding structures, so that you can kind of see the molecule as two equivalent halves. So for example, we have two double bonds in this structure, and the two double bonds are kind of sitting across from each other like this. And so visually, we can divide the molecule into halves. And to verify that this dividing line is, for example, a plane of symmetry, we need to make sure that the right half is exactly equivalent to the left half, and that the two halves will just exchange places upon reflection through the mirror plane. If we draw out the hydrogens explicitly, and we can put these kind of wherever we want to, and I'll actually draw the lone pair so that it's actually perfectly bisected by this line as well. What we can notice is that the left-hand half, the half over here, is exactly equivalent to the right-hand half, and reflection through a plane that is perpendicular to the screen, that's why I've drawn it as a line like this, reflection through this plane perpendicular to the screen leaves the molecule identical to the way it was before. So to verify this, let's draw the left half in blue and show what happens after reflection through this internal mirror plane. After we reflect through that plane, the blue half that's on the left is now on the right, so I'll kind of draw it this way. But of course, the colors that we draw are arbitrary, right? The appearance of the molecule is identical to the way it was before. And one last quick note about this, if I even consider the lone pair, The blue electron of the lone pair, if you like, is now on the right, and the black electron is on the left, but of course electrons are electrons, and so again, after reflection through that mirror plane, we end up with a structure that's identical to the starting structure. So this plane of symmetry is, in my opinion, a little bit more difficult to see than the planes of symmetry that are just the plane of the screen. One thing you should also note about this case is that the plane of the screen is not a plane of symmetry of this molecule. While it is true that a molecule may have more than one plane of symmetry and that you only need to find one to verify that a molecule is achiral, in this case, the plane of, say, the five-membered ring is not a plane of symmetry. Note that if we consider the plane of the screen, which is also the plane in which the atoms of the five-membered ring are sitting, reflection through this plane is going to move the nitrogen atom into the hydrogen atom and vice versa. They're going to exchange places. And that changes the configuration at this carbon right here. That changes the appearance of the molecule. Let's now look at the last two examples, which we already know are chiral. So let's start with the bottom left case. What happens when a molecule lacks a plane of symmetry? How can we rigorously verify that? Well, if you want to get technical, the only way to truly verify that is to look at every possible reflection plane and verify that it does in fact change the appearance of the molecule. Typically, however, it's straightforward to narrow down the possible candidate planes into a list of a few possibilities. And to start whittling down and finding these candidate planes, it's useful to do the same thing we did with the bottom right example. Look for corresponding structures. Structures that we know need to reflect into one another for these candidate planes of symmetry. So for example, we might look at these two hydrogen atoms as corresponding structures, or the CH2 groups on either side, here and here, as corresponding structures that need to reflect into one another upon reflection through a plane of symmetry. From these corresponding structures, we can generate some candidate planes of symmetry. So for example, if we want to reflect the two hydrogens into one another, we need to reflect through a plane that goes like this, perpendicular to the screen and kind of bisecting the carbon-carbon bond in the middle there. Is this a plane of symmetry? Does reflection through this plane leave everything else in the molecule unchanged? Well, if we think about what this reflection would do, we can see that it does not, in fact, leave everything in the molecule unchanged. Specifically, while the ring on the left would look identical, I'll just draw it overlaid to imagine the structure after the reflection. In the ring on the right, reflection is going to move the double bond down to this position. And so the blue molecule on top, the result of reflection through this plane, is not identical to the original structure. The blue plane is not a plane of symmetry. Finding even one difference between the structures before and after reflection allows us to conclude that this is not a plane of symmetry. So the blue plane is out. What about the CH2s on either side? Well, to reflect these into one another, we need to reflect through a plane that's perpendicular to the screen and that runs through the hydrogens. Such a plane will not change the positions of the hydrogens upon reflection, right? So this seems like a fairly promising candidate in that regard. Let's do the reflection and see where that leaves us. Well, the hydrogens, after reflection, remain in the same position. They're sitting on the plane, and so reflection just kind of flips the atoms over, but does not change their positions. The ring on the left, the six-membered ring on the left, is now over here. And the six-membered ring on the right, which contains the double bond, is now on the left. Have we changed the appearance of the molecule? Well, yes, we have. We've moved a double bond that was on the right-hand side over to the left-hand side upon reflection. The molecule is not identical in appearance after this reflection through the green plane. So that's out. This green plane that runs vertical is not a plane of symmetry of this molecule. So these two hypothetical planes we've ruled out as planes of symmetry. One other possible plane, which I'll leave to you as an exercise to verify that it's not a plane of symmetry, is the plane of the screen. Ignoring the intricate three-dimensional details of the two six-membered rings, which we can kind of average out anyway, reflection through the plane of the screen is not going to change the positions of the six-membered rings, but verify on your own why this plane is not a plane of symmetry of the molecule either. So we've tried a horizontal plane, a vertical plane, and the plane of the screen. None of these are planes of symmetry. In fact, there is no reflection plane that leaves the position of this double bond unchanged while leaving the positions of the hydrogens unchanged or exchanging their positions. As a result, the molecule lacks a plane of symmetry, and we can conclude that it's chiral. Finally, let's look at the top right case, which we also concluded was an example of a chiral molecule. Can we verify that this molecule lacks a plane of symmetry? In fact, we can. And just like we did for the last example, using this idea of corresponding structures, I think can help. It's evident, for example, that these two carbons need to either not move or need to be reflected into one another upon reflection through a potential plane of symmetry. Using these two carbons as corresponding structures, there are two potential planes of symmetry that come out of this. One is the angled plane that bisects this carbon-carbon bond, goes through the cyclopropane sort of point carbon, and also bisects the carbon-carbon double bond perpendicular to the screen like this. Is this a plane of symmetry? Well, It's not a bad one, right? Because reflection through that plane is going to exchange the positions of our two corresponding carbons. However, it will also have the effect of moving the methyl group from kind of the right-hand side of the molecule to the left-hand. And that's a problem because in the original structure, we have a hydrogen sitting there, not a CH3. So this angled plane is not a plane of symmetry. The other potential plane suggested by these corresponding carbons is the plane of the screen. That would leave the positions of those two carbons unchanged. However, you should notice that reflection through the plane of the screen is going to, for example, exchange the dashed hydrogen with the wedged carbon on both of these carbons. That too is an issue. The resulting structure after reflection through the plane of the screen leaves the appearance of the molecule different from the appearance of the original structure. Therefore, the plane of the screen is not a plane of symmetry either, and since there's no plane of reflection that moves these corresponding structures into each other or leaves their positions unchanged without messing with something else in the molecule, we can conclude that this molecule is chiral. So identifying the lack of a plane of symmetry within a molecule is a little bit tricky and takes some practice. But as you start to recognize where planes of symmetry are located in achiral molecules, your ability to recognize a lack of a plane of symmetry will be honed as well. While this method is not a failsafe in the sense that if you miss a plane of symmetry in an achiral molecule, you may call it chiral when it's in fact achiral, it's a quick method, and it works well in cases when you're pressed for time or you want to move quickly through the identification of a molecule as chiral or achiral. It'll also help you build up your pattern recognition apparatus because you'll start to recognize structural patterns that are independent of the atom types involved and just relate to the geometry of different types of molecules. So for example, pretty much all simple tetrahedral molecules